Okay, so now that we know how to anti-differentiate, we want to return to one of our applications of differentiation, which involved rates of change in kinematics. And so now that we can reverse the process of differentiation, it means that we can work backwards in problems involving rates of change in kinematics. So if we're given information about the rate, we can find information about the original quantities. So we know that, for example, if we've got, as this first example says, h and t, for example. So let's do height and time. We know that if we've got an equation for height in terms of time, when we differentiate that, what we're getting is the rate of change of the height with respect to time. But if we're given information about the rate of change, we can then obviously work backwards to find out the connection between h and t. So it works both ways. And the same with the kinematics. So we know kinematics, displacement, we differentiate displacement to get velocity, we differentiate velocity to get acceleration. So therefore, if we have acceleration, we can anti-differentiate that to get to velocity. If we have velocity, we can anti-differentiate that to get to displacement. So it is now just giving us a bit more flexibility about working with these problems involving rates of change in kinematics. Okay, so let's work through these. Examples here. So anti-differentiation can be relevant to problems involving rates of change if we are first given information about the rate, then asked to find information about the original quantities. So example 1 here, the rate of increase of the height, h centimetres, of a cylinder with respect to the radius is given by dhdr. So that's what dhdr is, the rate of change of height with respect to radius. And it is 3r squared minus 2. The height of the cylinder is 80 centimetres when the radius is 4 centimetres. Okay, so the first part of the question is to express h in terms of r. So we've got the derivative of h and we want to get h. And so we know h will be the antiderivative of the derivative. Now we're differentiating with respect to r, so therefore we anti-differentiate with respect to r, not with respect to x this time. So that means we're anti-differentiating 3r squared minus 2 with respect to r. Alright, antiderivative of 3r squared is 3r cubed on 3, so adding 1 to the power, dividing by that power, minus antiderivative of 2 becomes, now not 2x, careful because you're with respect to r, so it becomes 2r, and then plus c. Okay, so this isn't h in terms of r, this is h in terms of r and c, so there must be some information to allow us to find c, and that is that when the height of the cylinder is 80 centimetres when the radius is 4 centimetres. Okay, so we know when r equals 4, h equals 80, and so that means we get 80 equals, let's just simplify that 3 on 3, so that's just r cubed minus 2r plus c. So 80 equals 4 cubed minus 2 times 4, plus c. So 80 equals 4 cubed is 64, 2 times 4 is 8, 64 minus 8 is 56, and so c is 80 minus 56, which is 24. Alright, so therefore h is equal to r cubed minus 2r plus 24. So there's h in terms of r. And then in part B of the question, we want to find the height of the cylinder when the radius is 5. Okay, so we want h of 5. Okay, so this is h of r, h in terms of r. So h of 5 is 5 cubed minus 2 times 5 plus 24. 5 cubed is 125, minus 10 plus 24. 125 minus 10 is 115, and plus 24 is 139. So when the radius is 5 centimetres, the height is 139 centimetres. Part C, find the rate at which the height is increasing when the radius is 3. So find the rate, that's dh, dr, that's what we want to know. So we want to know when r is equal to 3, dhdr, So we've got dhdr back here, it's 3r squared minus 2 is going to be 3 times 3 squared minus 2. So that is, 9 times 3, so 27 minus 2, so that is 25. Now let's think about the units here. So it's dhdr, so units of height compared to units of radius, which are both in centimetres. This is centimetre per centimetre. So for every 1 centimetre change in the radius, we get a 25 centimetre change in the height. Find the average rate of change of the height as the radius increases from 1 centimetre to 3 centimetres. So remember, average rate of change is not to do with derivative. It is essentially the gradient of a straight line. So average rate of change of the height as it changes from as the radius changes from 1 to 3 is going to be h at 3 minus h at 1 over 3 minus 1. It's essentially rise over run. Change in the height over the change in the time. Okay, or change in the radius, I should say, sorry. So h of 3, okay, so let's work that out. I'll just work that out off to the side here. H of 3 is going to be 3 cubed minus 2 times 3 plus 24. So my function, remember, r cubed minus 2r plus 24. So that is 27 minus 6 plus 24, so that's 21 plus 24, so 45. And then h of 1 is 1 cubed minus 2 times 1 plus 24, so that's 1 minus 2 plus 24, sorry. So that's negative 1 plus 24, so that's going to be 23. Okay, so this is 45 minus 23 over 3 minus 1, which is 2. 45 minus 23 is 22 over 2, and so it is 11. It's a rate of change, an average rate of change, so the average rate of change is 11 centimetres per centimetre, units of height per units of radius. Okay. Alright, and as we mentioned earlier too, one of the more common applications of rates of change is the study of the motion of a particle. We call this kinematics, and kinematics deals with 3 quantities associated with motion: displacement, velocity, and acceleration. So previously, when we've been differentiating, we've looked at how to move in this direction. So if we have displacement, we differentiate to get velocity. If we have velocity, we differentiate to get acceleration. But now we can move in reverse. If we want to know the velocity, we can anti-differentiate the acceleration. If we want to know the displacement, we can anti-differentiate the velocity. Okay, so let's have a look at a question. A stone is projected vertically upward from the top of a 20-metre high building with an initial velocity of 15 metres per second. For this problem, it can be assumed that acceleration due to gravity is approximately negative 10 metres per second squared. Now, it's more like negative 9.8 metres per second squared, but just so we can do the maths by hand, we'll stick with negative 10 as an approximation for acceleration. Okay, so we're given the acceleration. It's constant acceleration. So the acceleration with respect to time is always negative 10. Doesn't matter what the time is, it's always going to be negative 10. So we want the velocity. Velocity is the antiderivative of the acceleration. Sorry, not with respect to x, with respect to t. And so that is the antiderivative of negative 10. So we know when we antidifferentiate a constant value, we get negative 10 times t, and then plus c. Alright, so then we want to think about, let's just see if I can fit that all in there actually. Let me just do this for a minute. Okay, so then we want to think about, we're given information about the initial velocity, okay? So we know that v of 0 is equal to 15. So when t equals 0, the velocity is 15. So v of 0 will be negative 10 times 0 plus c. We know that's 15, and so therefore c is equal to 15. And so therefore our velocity equation, velocity in terms of time, is negative 10t plus 15. Okay, then part B, we want to find x of t, the displacement in terms of t. Alright, so x of t is the antiderivative of the velocity with respect to t. So that's the antiderivative of negative 10t plus 15 with respect to t. So antiderivative of negative 10t is negative 10t squared on 2, so that's negative 5t squared plus 15t plus c. Okay, so then we also know that the stone is projected vertically upwards from the top of a 20-metre high building. Okay, so that's about the initial displacement. So this tells us that initial velocity is 15. Now this tells us about the initial displacement. Now technically, actually, you would need a bit more information for you to be precise about this, but as long as you're consistent with how you interpret the displacement, you will get all the right answers after here. You just get a slightly different displacement equation. So let's just talk about what the options are here. So we've got a building that we know is 20 meters tall, okay, and we're projecting a stone vertically from the top of here. So it goes up and then it drops back down and it can potentially come back down to the ground, okay. It's just going straight up and down. So most kinematics, we only in methods only deal with motion in a straight line. So it's just going up and down. So you can either measure your displacement from the ground, okay, which would be fine, which would then mean, if that's what happens, that would mean your initial displacement, sorry, I should have drawn that. Let me move it over the other side so I've got room. Okay, so if you measure it that way, you would say that your initial displacement is 20, okay. The other way that you could measure it, and we'll have a look, I'll show you that it gives you the same thing. We'll do it one way, but then I'll have to come back and have a look at the other way. You could instead measure this as being zero displacement, okay, which would then mean the ground is displacement of negative 20. Okay, so you just need to be consistent about how you define your displacement. I'm going to define the displacement relative to the ground. I'm going to use the purple structure. I think that's easier. I'll come back and have a look at what happens if we do it the other way. So I'm going to say that that x of 0 is equal to 20. My initial displacement is 20. Alright, so let's use that. So if we know that x of 0 is going to be 0 plus 0 plus c, we know that's 20, and so therefore c is 20, and so therefore, sorry, let me move that again, forgot that we still had to write more there. Okay, and so therefore x of t is equal to negative 5t squared plus 15t plus 20. Now, if you're given information about the initial displacement or velocity, then that thing will automatically be the c value, but I want you to be explicit about how you're finding that c equals 20. I'm using the fact that when t is 0, c is x is 20, and that makes c 20, and so therefore I can get my function. So don't ignore that key kind of process step. And again, it's a bit like, yeah, we'll talk later on in this topic. There are some issues with the fact that we only deal with anti-differentiating polynomial functions in year 11. So obviously, if you sub t equals 0 into a polynomial, you always just get the constant value. But if the function is you know, cos of x, then cos of 0 isn't 0. So you need to sort of still maintain that process of I'm subbing in 0 and then using that to find c. Okay, find the time taken for the stone to reach its maximum height. Okay, so maximum height will be when stone turns around, which means we'll have 0 velocity at that point, and so we want to solve v of t equals 0. Okay, so our velocity equation was negative 10t plus 15 when that equals 0, so 10t equals 15, t equals 15 on 10, which is 1.5 or 3 on 2. What's our units of time? Seconds. So the acceleration is given in meters per second squared, so all the distances are in meters and the times are in seconds. Okay, so it takes the stone 1.5 seconds or 3 on 2 seconds to reach its maximum height. Find the maximum height reached by the stone. So now we know that this is when t equals 3 on 2. Okay, and so we want to find what is the position of the particle at that point. So we want to know x of 3 on 2. So let's do our negative 5 times 3 on 2 squared plus 15 times 3 on 2 plus, what's c again, 20? Okay, so that's negative 5 times 9 on 4 plus 45 on 2 plus 20. Let's get a common denominator there. So that's negative 45 on 4, plus this is 90 on 4, and then this is 80 on 4. So negative 45 plus 90 is 45, plus 80 is 125 on 4, okay? Or that would be, what's that going to be? 120 divided by 4 is, 124 divided by 4 would be 31, so it'd be 31 and a quarter. But you can leave it as a fraction, that's fine, as long as it's a simplified improper fraction. There's no problem with that. So the maximum height reached by the stone is 31.25 metres. Now this is where it's advantageous that I've defined my displacement as being relative to the ground, because that means when I've worked out the displacement at 3 on 2, that is a displacement from the ground, and so therefore it's a height. Okay, so if I'll work back through the question in a minute, looking at what would happen if we defined our displacement differently. But I think the most logical thing is to define the displacement relative to, you know, an obvious place. So the two most obvious places would be the ground, which is what we did, or relative to where the stone begins. But then you need a bit more interpretation in your answers. And as I said, I'll work back through it with that. How long does it take for the stone to reach the ground? Okay, so when the stone reaches the ground, let me just move my diagram down a bit further so I can... When the stone reaches the ground, that is when, in my problem, that is when the displacement, that is when the displacement is 0. Okay, so we want to know what is the time, what is t, when x is equal to 0. Okay, so here we want to know x of t equals 0. 0 when is 0 displacement? So our displacement function again is negative 5t squared plus 15t plus 20 equals 0. Let's divide everything by negative 5. So that's t squared minus 3t plus 4. Factors of 4 that add up to negative 3. They don't exist, do they? Just checking that I've got my function right. Minus 15t plus 20. Yeah, so it's not going to be a nice whole number answer here, so I'm going to use my CAS. Let me just check that I've done that correctly. Minus 5t added... Right, sorry, I've realised my error. So down here when I divided by negative 5, that should have been minus 4. Okay, so factors of negative 4 that add up to negative 3, so that'd be t minus 4 and t plus 1. And so therefore t equals 4 or negative 1, but obviously time is positive. So t equals 4. So it takes 4 seconds for the stone to reach the ground. What is the velocity of the stone as it hits the ground? So we want to know what is the velocity after 4 seconds. And so our velocity was negative 10t plus 15. So negative 40 plus 15. So negative 25 meters per second. So it makes sense that it's negative velocity as it's heading to the ground. We're going in a negative displacement direction. And it's going fairly quickly. Find the average velocity of the stone during the first 4 seconds. Okay, so average velocity is change in displacement over change in time. So it's the displacement after 4 seconds minus the displacement at the beginning over the change in the time. Okay. So the change in the displacement, so we already know that the displacement after 4 seconds is 0. Okay, that's what we already know that. Minus the initial displacement, which was 20, over 4, so negative 20 on 4, so that's going to be negative 5 meters per second. So the average velocity is negative 5 meters per second. It makes sense that over the first 4 seconds, so the first 4 seconds is the entire up to its maximum and then down to the ground. It makes sense that the average velocity over that period is negative because it's traveling further with negative velocity, so it's going down more than it's going up, okay? And so therefore the average velocity should certainly be negative. Find the average speed of the stone during the first 4 seconds. Okay, so average speed is distance over time. Oops. So we need to be able to work out the distance. Unfortunately, we've got, as we've worked through this problem, we've got a really clear picture of what's happening with the particle. So we know that at the turning point, we know that that displacement was 31.25 meters. So we know that it goes from 20 up to 31.25, so that's 11.25, and then it drops the 31.25 meters down to the ground. Okay, so the distance is going to be 11.25, which is the travelling up to the turning point, plus then 31.25 as it travels down to the ground in the first second over the 4 seconds. So, sorry, I'll try and do this without my CAS. We'll go back through the CAS in a second. So 11.25 plus, so 11 plus 31 is 42, and then 2 lots of 0.25 is 0.5. So it's 42.5, sorry, 42.5 on 4. What can we do there? We could double the top and the bottom if we want, so that's going to be 85 on 4. Okay, which if you want, that is 21 and a quarter, 21.25. Okay. All right, 21.25. Sorry, it's a speed, so meters per second. Okay, so it's not just about making your average velocity positive. You have to think separately about distance over time. Average velocity is displacement over time, and the displacement in the first 4 seconds is just negative 20 meters. Okay, so that's because essentially you're just looking at the difference between where it started and where it finished. So it starts here, and it finishes here. And so that displacement is negative 20, okay? But that's not connected to the distance because it doesn't take into account the fact that it went up and came back. All right, before we finish off the video, let's just go back up here to if I had completely defined this problem separately as instead saying that the initial displacement, okay, if I had instead said that we're going to measure displacement from here. Okay, so therefore this would be displacement of negative 20. Okay, that would mean when you found your displacement equation, which was here in part B, you would have had no plus 20 here because initial displacement was 0. Okay, then when you found the maximum height, time the maximum height, that's fine. Okay, then when you subbed x equals 3 on 2 into your displacement equation to find the maximum height, you would have found that the maximum height was only 11.25 meters because you wouldn't have had the plus 20 on the end, but that wasn't giving you maximum height. That was giving you the displacement relative to where you threw it from. So then you need to add on the height of the building and know that the maximum height of the building is 11.25 plus 20. Okay, but the displacement, so here you're finding when t equals 1.5, your displacement is 11.25, but that's not equivalent to height because we've defined the displacement from here, from the top of the building. So you just need to then interpret your equation, which still means that the building is 20 plus 11.25 meters tall. Sorry, not the building, the max height. .25 meters. So you would need that extra step at the end to interpret your answer. Okay, and then how long does it take for the stone to reach the ground? So this time you wouldn't be solving, the ground is not displacement of 0, the ground would be displacement of negative 20. So you wouldn't have had the 20 there, but you'd have had negative 20 here, so you then still end up with the same equation. Okay, and then the velocity when the stone hits the ground, that's no different. Your velocity equation doesn't change. Average velocity, average speed. You just need to think a bit about your distances a bit differently. So it all still works out if you define the displacement differently, but I think in this problem it was much easier to go with what we did the first time around, which was to define the displacement as being relative to the ground. So that's x equals 0 on the ground, which then meant that every single displacement you found was giving you a height. Okay, so there was no sort of added interpretation. But the problem still works completely if you define the displacement slightly differently, as long as you're completely consistent about how you then apply your displacement function. Okay, so the work today is in 2 places. The first is a worksheet on rates of change involving antidifferentiation, and then the second is from the textbook exercise 18G, which is going to be kinematics problems involving antidifferentiation.